Hi class. In this video, we're going to start chapter 8, which is on sampling distributions, and section 8.1 is talking about distribution of the sample mean, right? So I have here just just a quick recap about, what we're doing is we want to recall that we're generally interested in population parameters, but these are often really hard, difficult, impossible, and or expensive to obtain, right? So instead, what we do is we collect samples uh, and calculate sample statistics, and we use statistical methodologies to study and try to guess what's going on, estimate what's going on with the population, right? So that's why this this class and this field of study is called statistics, right? Because we study statistics, but really what we're interested in is what's going on in the population. Right. So before we get started with some examples, I have just some definitions and some ideas to discuss. So first thing, a definition. So the sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample of size n, right? And then a sampling distribution of the sample mean x bar is the probability distribution of all possible values of the random variable x bar computed from a sample of size n from a population with mean mu and standard deviation sigma, right? So basically what the idea is with this section is we're going to say we get a specific sample size, right? So let me come over here. Right. So let's say we're looking at height of adult males, let's say. Right. So, this could be, normally distributed. Maybe we find that the mean is roughly, I don't know, 55 inches, and the standard deviation of mean height of adult males, let's say, is 5 inches. Right? I'm not sure if these are accurate with mean and standard deviation of adult males, but just to give an example here, right? So far what we've been discussing and studying is looking at this. If this is normally distributed, we know in the center is going to be the mean 55 inches, and we've talked about like the empirical rule. So if I go out, to the right, one standard deviation, which is 5 inches, this would be 60, and go backwards 5 inches, this would be 50, right? And then go out again, we would have 65, and then to the left, 5 inches would be 45, right? And then we could go one more, right? And so this would be 70, and this would be 40, right? And we've talked about like the empirical rule, where if you're within one standard deviation of the mean, right, we would expect 68% of my data, right? So this is my mean. This is the mean plus one standard deviation. This is the mean minus a standard deviation, right? And so forth. And then if we go two standard deviations out, right? So if I go between 45 and 65, we would expect, 95% of my data. And then if you're within three standard deviations, right, we would expect 99.7% of the data, right? So remember, this is called the empirical rule. Right. So that's one idea we've talked about with this. Another idea is, given this information and we know that that the population is normally distributed, what's the probability of randomly selecting a male who's taller than 60 inches, right? So we could begin to calculate this, right? So we could draw a normal distribution. I know in the center is going to be my mean of 55, and somewhere over here is going to be 60. So I'm trying to find what's this area here. This area is going to be equal to the probability that x is greater than or equal to 60. right? And we can use StatCrunch to calculate that area, and we've looked at that multiple times so far. So the important thing to think about here is that my data, my distribution, I would label this with just an X here because, my data is just on one person, right? So this data is on individuals, right? So what we're switching focus in on is studying how samples are going to vary, right? So in other words, if I'm still looking at, adult male height, right? So height of adult males, right? Then we're going to pick a sample size, let's say n equals 5, right? So the idea is I'm going to get one sample, sample number 1. I'm going to get 5, randomly select 5 males to be in this group, right? Let's say we have, someone who's, 61 inches, 60 inches, 58, 50 inches, and 61 inches, right? And then what I can do is I can compute a mean of this sample, right, which would be x bar. So I would add them up, right? So I would take 61 plus 60 plus 58 plus 50 plus 61, and then divide by 5, and I get 58, right? So the mean of this sample is 58. Well, what if I pick another sample, get a second sample, randomly selected from the population? Maybe I get 50, 62, 70, 55, 59, right? And then I can calculate another sample mean. So we get 50 plus 62 plus 70 plus 55 plus 59. Divide that by 5, and I get 59.2, right? So notice that these vary, and it makes sense that these would vary because if I, pick different 5 people or 5 people with, different heights, the sample mean is going to vary, right? So what we want to study is, well, how does this vary, right? So when I drew a normal distribution up here, remember this was on individuals, right? And I label the axis capital X, right? Because that's my random variable, right? So what we're going to be looking at now is thinking about having a normal distribution still, but instead of X studying the individuals, we're studying the means of the samples of size n equals 5, right, in this case. So, around the center, we're still going to have a mean, right? And then the individual parts inside of here are x bars, right? Not x's. So, this sample of 5 people is going to live, in the data set. This sample is going to live in the data set. So we're studying sample means and how those are distributed, right? So it's a slightly different focus. So the mean, so in order to study this, right, we need to know what the mean and standard deviation is going to look like for the sampling distribution of x bar, right? So suppose that a simple random sample of size n is drawn from a population with mean mu and standard deviation sigma. The sampling distribution of x bar has mean, the mean is going to be equal to mu, the population mean, and the standard deviation is going to be equal to the population standard deviation divided by square root of n, right? So it turns out that the standard deviation of the sampling distribution of the sample mean is going to be less than the population standard deviation. In other words, there's less variability, right? And this makes sense because, when you're looking at the variability of the whole population versus, like my past example, me just picking 5 people, right? There's going to be less variation between those people, right? And so since it's calculated calculated differently, we refer to this as standard error of the mean, right? So the standard deviation of the sampling distribution of x bar is called the standard error of the mean, right? But it behaves similarly to standard deviation, right? So if you add a standard error to the mean to the left and right, then we expect 68% of my data, right? So like the empirical rule, right? So all of those kind of things would still apply, right? Um, and this is just some in other words. So, regardless of the distribution of the population, the sampling distribution of x bar will have a mean equal to the mean of the population and a standard deviation equal to the standard deviation of the population divided by the square root of the sample size, right? So it doesn't matter what the distribution is. We expect those two things to happen, right? For the means to match and the standard deviation to be the population standard deviation divided by the square root of your sample size, right? So in this first part, what we're going to do is look at, well, what if your population distribution, your x, is normal? What's that gonna do to the distribution of x bar? And then we're also going to study that. Well, what happens if your population is not normal, right? Maybe it's skewed. What does that mean, right? So if a random variable x is approximately normally distributed, the sampling distribution of the sample mean is going to be approximately normally distributed, right? So here in Figure 4, you can just see, in context what we've looked at. So the blue part is the population distribution, right? So that's x, and then this like pink color is the sample mean distribution, right? So that's labeled x bar. So notice that they're centered about the same spot, right? So that means that their means are equal, like we said. And then if you take a look at their standard deviations over here, right? Notice that the standard deviation of the population is 15, and the standard deviation of x bar is 15 divided by square root of 9, and that's going to cause that to be smaller, right? So 15 divided by square root of 9, so square root of 9 is equal to 3, right? So this would be, equal to, let me just write down here, right? So sigma x bar is equal to 15 over square root of 9, which would be equal to 15 over 3, right? Square root of 9 is 3. So that's just equal to 5, right? And that's clearly less than 15, right? Which is sigma, the standard deviation of the population, right? So you can see that that's going to be true based on their numbers, but also of their graph, right? So remember, a smaller standard deviation, it means the numbers, the values are going to be closer together. So you end up with like a taller, skinnier graph, right? Where if your variation is more spread out, then you kind of have like a shorter, fatter graph, right? Which is like the blue, right? And then here, these are some conditions that or two assumptions that we make when using these methods. So in statistics, when you have various statistical tests, there's always going to be some kind of assumptions that we're making for that test to be for that test to work, right? So you need to test the assumptions, and if the assumptions are met, if you study statistics more and more, you'll learn like how to deal with that or how to account for that, right? So we want the assumptions to be met, so that way we're calculating like accurate values, right? So the two assumptions we're making is, one, the sample must be a random sample, right? So we need to be randomly selecting the sample. And then number two is that the sample values must be independent, right? So in order to check that, we have this condition where we want our sample size to be less than 5% of the population, right? So if that condition is true and also the sample is random, then we met those conditions. All right. So in example 1, we're just practicing here using the equations. So we have mu of x bar equal to, so this is just equal to the mean, which is 80, and sigma of the sampling distribution is equal to sigma divided by square root of n, right? So plugging these values in, I would have 14 over the square root of 49, which is equal to 14 divided by square root of 49 is 7, and 14 divided by 7 is 2, right? So just practicing using those equations. So when you have the subscripts x bar, right, that's referring to the mean and standard deviation of the distribution of x bar. Right. So then example 2, it says the upper leg of a 20 to 29-year-old male is approximately normal with a mean length of 43.7 centimeters, right? So mu is 43.7 centimeters, and a standard deviation is equal to 4.2 centimeters, right? And we're told that the that this variable is approximately normal. So the population is approximately normal. So since our sample comes from a population that's approximately normal, remember we expect the sampling distribution of x bar to be approximately normal as well, right? So in part A, we're looking at, well, what's the probability that I randomly select a 20 to 29-year-old male that has an upper leg length that is less than 40 centimeters, right? So it's important in part A to understand that here we're talking about the probability of randomly selecting one male, right? So that's what we've talked about before, just talking about one individual, right? So my picture, on my axis is just going to be labeled x, right? And in the center, we're still going to have the mean, which is 43.7, and I'm trying to find what's the probability of randomly selecting one male that has an upper leg that's less than 40 centimeters, right? So somewhere over here to the left is going to be 40. I'm finding the probability less than, so we're looking for this area, right? So I'm going to know what's the probability that x is less than or equal to 40, right? Where I have a mean of 43.7 and a standard deviation of 4.2. Right? So remember, we can find that using the normal calculator in StatCrunch, right? So I already have that pulled up. So I need to change my mean to 43.7, standard deviation to 4.2, and we want to find the probability less than 40. So hit compute, and we get that area, right? So I can write that down. So the probability of randomly selecting a 20 to 29-year-old male that has an upper leg length less than 40 centimeters is 0.1892. Right. So then part B, it says a random sample of 9 males who are 20 to 29 years old is obtained. What is the probability that the mean upper leg length is less than 40 centimeters, right? So in this case, I'm selecting samples of size n equals 9, and I want to know what's the probability that I pick a sample where x bar is less than 40 centimeters, right? So this is a little different story here, right? The sketch of the graph is going to look similar, right? And it's important to note that if we were, actually drawing this accurately rather than just like a rough sketch, or generating this on a computer, if we put the graphs from part A and B over top of each other, they would look differently, right? Because in part B, the standard deviation is going to be different, right? So up here, the standard deviation is 4.2, where down here in part B, we would have the mean of x bar is equal to mu, which is equal to 43.7 still, but the standard deviation is equal to sigma divided by the square root of n, right? So this would be 4.2 divided by the square root of 9, right, because our sample size is 9, which is equal to 4.2 divided by 3, which that is equal to 1.4. Right, so 1.4 is significantly smaller than 4.2. So if we put those graphs over top of each other, the graph of part B, right, would look more like this pink line, right? So it's going to be taller, skinnier, has a lot less standard deviation, and the population, is gonna look like that, right? So just because you have a normal population, it doesn't mean their graphs look alike, right? That's why we have to pay attention to what's the mean, what's the standard deviation, so that way we can calculate the area appropriately, right? So, and the label, the axis, this should be labeled x bar, right? Because we're looking at a sampling distribution in this case. And we're still trying to find, what's the probability that x bar is less than or equal to 40, right? So notice also we use a different variable inside of there, right? Because we're talking about x bar, a sample mean versus the value of one particular individual, right? So this is, if I randomly select 9 people at a time, what's the probability that my sample has a mean that's less than 40, right? So over here somewhere would be 40. And then here's the shading of the area that I'm trying to find, right? So I could use StatCrunch to calculate this. So I need to change my standard deviation to be 1.4. And I'm still trying to find the probability that x is less than 40. My mean's the same, right? So the only thing that changed was the standard deviation. Right? So if I hit compute, get that probability, right? So it's about 0.0041. Right, and this number is approximately equal to 0.004, which is equal to 4 out of 1,000. Right? So if we think about it in this terms, right, the idea, the interpretation of this number is if I randomly picked 9 people and calculated the sample mean, and I did it again and again and again until I had 1,000 of these sample means, right? What this number means is that out of 1,000, about 4 of them are going to have a sample mean less than or equal to 40, right? That's the idea of what that number means, right? So then in part C, it's very similar to part B. The only thing we're changing is the sample size, right? So in part C, n is now 12, right? So the mean of the sampling distribution is still going to be equal to mu, which is 43.7. Sigma of the distribution would be equal to sigma over the square root of n, which is equal to 4.2 divided by the square root of 12, which this is approximately equal to 1.2124, right, if you plug that in your calculator. And my caution here is to go to 4 decimal places when you're looking at calculating sigma, right? In part B it came out nicely to be exactly 1.4, right? There was no rounding needed. But when you need to round, if you go to 4 decimal spots, it'll just help you be more accurate, right, when you're using StatCrunch. Right, so then can draw my distribution. In the center would be my mean of 43.7, and I'm still looking for the probability that x bar is less than or equal to 40, right? The difference was we changed the number of people and the sample size, which made a smaller standard deviation yet again, right? So this probability we would expect to be smaller, right? So if I go to StatCrunch, the only thing I need to change is the standard deviation to be 1.2124. Hit compute, and as we expected, it's really tiny, right? In fact, on the graph, it doesn't even really show up on the graph, right? The shaded region. So this is equal to 0.0011. Okay? So really small. So it's definitely smaller than before, right? So in part D, we want to think about how to changing that sample size between part B and C. How did that impact the probability, right? So increasing the sample size decreases the probability that X bar is less than 40, right? This happens because sigma of X bar decreases as n increases. Right? So in other words, if you think about the equation for sigma of X bar, that's equal to sigma divided by square root of n. Right? So what we're talking about doing is leaving this number the same. Right? And we're changing n. What happens to the standard deviation? Right? So as n gets bigger, you're dividing by a bigger number, which in turn makes sigma smaller, right? Because if you take like 5 divided by 20 versus 5 divided by 2,000, right? If your numerator stays the same, and then your denominator gets bigger, then your overall number gets smaller, right? So, 5 over 20 is bigger than 5 over 2,000. Right? And then so if you think about what happens to your distribution shape, right? So like here, if you think about this blue line, right, this has a bigger standard deviation. The pink line has a smaller standard deviation, right? So when you get a smaller standard deviation, your graph's going to be like taller and skinnier, right? So then if I look at, what's this area going to be that I'm shading in red? Well, you can imagine that the area in the taller, skinnier curve is going to be a lot less than the area in the blue curve, right? Because there's more area under the blue curve, right, versus the pink, right? So since that has that effect on it, you're going to have less area, and the area under the curve corresponds to the probability, so that means your probability is less, right? So that's kind of the general idea with that question and why that works that way. Right. So then in part E, it says a random sample of 15 males who are 20 to 29 years old result in a mean upper leg length of 46 centimeters. Do you find this result unusual, and why? Right. So with this one, right, we can think about this. So we have a sample size of 15, and we get an X bar equal to 46, and I want to know, is this unusual? Right? So you might be thinking, well, let's calculate the probability that X bar equals 46, right? Well, since this is a continuous distribution, remember the probability at a particular value is just going to be equal to 0, right? So that's not helpful, right? So we can't really do that. What we can do instead is, here's my sampling distribution of X bar, and the center is going to be the mean, 43.7, and somewhere over here is going to be 46, the value I'm interested in. So what if I calculate what's the probability of being 46 or higher, and see if that's irregular, right? So remember, for continuous variables, we need to calculate the probability over an interval, right? So in other words, if I think about what's the probability of x bar being bigger than or equal to 46, and if this is less than 0.05, then we would conclude that it's unusual. Right? So first, we need to know the mean of the distribution and the standard deviation. So the mean would be equal to mu, which is equal to 43.7 still. The standard deviation would be equal to sigma divided by square root of n, which is equal to 4.2 divided by the square root of 15. Right? Plug that in your calculator. That's going to be approximately equal to 1.0844. So now we're ready to calculate that area. So I need to change the standard deviation to be 1.0844. We're looking at x greater than 46, and we can find that area. So if I round just to 2 decimal places here, it's about 0.02. Right? So this probability that x bar is greater than or equal to 46 is about 0.02, which of course is less than 0.05. So we would conclude that this is unusual. Right? So it's very unusual to get a sample mean that high, right? 46 or higher. Right? So then now what we want to discuss, so far we were looking at, well, what happens if the population is normally distributed, right? Now let's think about, well, what happens if the sample that the sampling is done from a population that's not normally distributed, right? So something that's important to understand is that the central limit theorem says that regardless of the shape of the underlying population, the sampling distribution of x bar becomes approximately normal as the sample size n increases, right? Also, some other things is that the central limit theorem talks about the shape of what x bar is going to look like. It doesn't talk about the mean or standard deviation, right? So the mean and standard deviation, those equations are still going to remain the same regardless of the shape of the population. But the central limit theorem, what it allows us to do is think about as n gets bigger, then the sampling distribution of x bar is going to be more and more normal, right? So if we look on the next page, top of the next page, actually take a look at this. So this is figure 10 from the textbook. So this first histogram, this is the relative frequency histogram, right, is of household income, right? So this is the population. And notice this is right skewed, right? So then this next relative frequency histogram is looking at, well, what's the distribution like if n equals 4, right? So I'm picking a sample of 4 random people and writing down its sample mean. Picking another 4, writing down its sample mean. Another 4, picking out its sample mean, and so forth. And this is the distribution shape I get. And notice we have a normal curve graphed on top of it, so we can see, how they compare. And this does not, it looks more normal than the population, but it's still not quite, doesn't look very normal. Still looks pretty right skewed, right? So we went from n equals 4 down to n equals 10 in this next histogram. And you can see that it's looking more and more normal, right? And then lastly, we look at n equals 25, and that looks pretty normal, right? It's very, very spot on, right? There's not a lot of blue on the outside of the curve, and very little white, a lot less white underneath the curve, right? So in other words, that normal model is going to do a lot better job approximating the probabilities if n is large, right? So notice it took about n equals 25 for it to look pretty normal. And some textbooks actually use that as the cutoff, is that they want an n to be greater than or equal to 25 in order to be able to use a normal model. but our textbook uses bigger than 30, right? So that's a condition, an additional condition if your population is not normal, right? So if I know that my population is normally distributed or approximately normally distributed, I don't worry about the sample size. I can use the normal model to estimate probability with X bar, right? But if your population is not normal, so maybe skewed, uniform, so forth, or bimodal, it could be look differently. Or if you don't know, then that's where we need n to be greater than or equal to 30. Right, so this is a condition. If your population is not normally distributed, right? And here's just a summary table of what we looked at, and just remember the equations for the center and spread are going to be the same, right? Identical. Right. So now let's look at example 3. So in example 3, we're asked to answer the following questions of the sampling distribution of the sample mean shown below. So I have this graph here of the normal model, and it's labeled here. So again, it's assumed that this is the mean plus 1 standard deviation, and this is the mean minus 1 standard deviation, right? But notice this is of X bar, right? So we should put X bar subscript here, just so we understand that we're not talking about the mean standard deviation of the population, but of the sampling distribution, right? And that's shown here, right? It's labeled X bar. That's how you can tell. So in part A, we're asked, well, what's the value of the mean of X bar, right? So that would be this guy right in the middle, right? In the center, that's where that's going to line up. So this would be equal to 12. And then if you want to find the value of sigma X bar, you're essentially just looking at the difference between those two, right? So sigma of X bar would be equal to 12.05 minus 12, which is equal to 0.05, right? So the standard deviation of X bar is 0.05. And then part C says if the sample size is n equals 9, what is likely true about the shape of the population, right? So since the X bar is following a normal model and my n value is less than 30, right? N equals 9, which is less than 30, then what that tells me is that the population must be normally distributed. Right? Because remember, that happens when your population is already normally distributed. And then in part D, it says if the sample size is 9, what is the standard deviation of the population from which the sample was drawn, right? So in other words, we're using this equation to solve for sigma, right? So I know that sigma X bar was equal to 0.05. Right, we calculated that in part B, right? And then I have sigma, and then we have square root of 9 and for n, right? So square root of 9 is 3, so we'd have 0.05 equals sigma divided by 3. So I can multiply both sides by 3, and I get 0.15 is equal to sigma. Right? So we're just solving that equation, right? So on the next page, this is example number 4. Right, so it looks like this just didn't pull down. So we're told that a simple random sample of size n equals 12 is obtained from a population with mean of 64 and sigma of 17. In part A, it says what must be true regarding the distribution of the population in order to use a normal model to compute probabilities involving the sample mean. Assume that this condition is true. Describe the sampling distribution of X bar. Right? So if we pay attention to what n is equal to 12, which is less than 30, right? So that tells me that the population must be normally distributed, right? So the population must be normally distributed. Right? So if that condition is true, then the sampling distribution of x bar will be approximately normal. With a mean equal to mu, which would be 64, and the standard deviation of x bar would be equal to sigma divided by the square root of n, which would be equal to 17 divided by the square root of 12, right? And this is approximately 4.9075, right? So those two numbers, right, the reason why we say those along with it is that tells what the graph looks like. Right, just like if you said, something looked to be a linear shape, right, you'd want to know the slope and the y-intercept, right? It kind of gives some information about what the graph looks like. So then in part B, it says, assuming that the requirement in part A is satisfied, determine the probability that x bar is less than or equal to 67.3, right? So I'm trying to calculate what's the probability that x bar is less than 67.3. So in the center is going to be my mean of 64, and I'm looking at, over here would be 67.3, and I want to know what's the probability that x bar is less than this value, right? So that's going to be shaded to the left. So that's the area that I want to find, right? So I can calculate this using StatCrunch. So we need to input the mean, which is 64. The standard deviation we found in part A to be 4.9075. So I'm trying to find the probability that x is less than 67.3. Hit compute, and we get that area, right? So it's really high, right? About 75%. So, and this is, this is pretty close to be 0.75, which is equal to 75 out of 100, right? So we could say, if we took 100 simple random samples of size n equals 12 from a population that is normally distributed with a mean of 64 and standard deviation of standard deviation of 17, then about 75 of the samples will result in a mean that is less than 67.3. Right? Remember, that's what those numbers represent. Right? So if we took 100 of these, about 75 of them would be less than 67.3. So then part C, we want to use the same distribution, but we're finding the probability that x bar is greater than or equal to 65.2. Right, so right in the center would be 64 still. Somewhere to the right would be 65.2. And I'm finding the probability greater than or equal to, so that's shading to the right. Right? So if you use StatCrunch to find this, you should get that this is equal to 0.403. Right? All right. So let's look at example 5 now. So example 5 says the shape of the distribution of the time required to get an oil change at a 10-minute oil change facility is skewed right. All right, so let me just write that down. So the population is skewed right. And then we're told, however, records indicate that the mean time for an oil change is 11.4, and the standard deviation for an oil change is 3.2 minutes, right? So I'm just labeling those values. So then in part A, it says to compute probabilities regarding the sample mean using the normal model, what size sample should be required, right? So since the population is skewed right, i.e. not normal, n should be greater than or equal to 30, right? So that will give us approximately a normal distribution then if n is bigger than or equal to 30. So in part B, it says, what's the probability that a random sample of n equals 40 oil changes results in a sample mean time of less than 10 minutes, right? So n equals 40. We need to calculate the mean of the sampling distribution, which would be equal to mu, which is 11.4. And then I need to calculate the standard deviation of x bar, which is equal to sigma divided by square root of n. Right, so n is 40, so I can plug that in. And sigma, which is up here, is 3.2. Right, so if I round that to 4 decimal places, this comes out to be approximately 0.5060. Right, and I put that 0 at the end because it rounds to that, right? So now that we know that, what we're trying to find is what's the probability that x bar, that I get a sample that has a mean less than or equal to 10. Right, so if you want to draw this, in the center is going to be the mean of 11.4, and we're trying to find over here the cutoff of 10. Oops. And this is x bar, so I'll label that distribution of x bar. So we want to find the probability to the left of x bar less than or equal to 10. So shade to the left. Right, so using StatCrunch, right, we just need to plug in my mean, plug in my standard deviation, and then probability less than 10. Hit compute, and I get that area. So it's 0.0028, right? And this, of course, is approximately 0.003, which is equal to 3 out of 1,000, right? So we could say if we take 1,000 simple random samples of size n equals 40 oil changes, then about 3 of the samples will result in a mean time of less than 10 minutes. Right? Right. So then part C says, suppose the manager agrees to pay each employee a $50 bonus if they meet a certain goal. On a typical Saturday, the oil change facility will perform 40 oil changes between 10 a.m. and 12 p.m., treating this as a random sample. What mean oil change time would there be a 10% chance of being at or below? Right? So in this case, my mean deviation is going to stay the same, right? But what we're doing is kind of like the inverse of finding the probability, right? Finding the area. So if this is my distribution of x bar and the center is going to be 11.4, I want the area to the left of some value to be equal to 0.1, right? 10%. And so I need to find this cutoff value for X bar that makes that happen, right? And that's going to be the goal that the manager wants to get. Right? Trying to push it down lower. Have my employees do the oil changes quicker. So in this case, the mean standard deviation would stay the same, and the less than would stay the same, but I need to change this area to be 0.1. And if I hit compute, I get about 10.75. Right, so this X bar, 11.75, or 10.75. All right, so we just have one more example to look at. This one is looking at ATM withdrawal data. So it says, according to Crown ATM Network, the mean ATM withdrawal is $67. And the standard deviation we're assuming to be equal to $35. Right? So in part A, it says, do you think the variable ATM withdrawal is normally distributed? If not, what shape would you expect the variable to have? Right? So, this might take some time to think about, but, if you really think closely about this, about, what kind of distribution shape would we think that ATM withdrawals would look like? So the way I think about it is, a lot of people, when they go to the ATM, they might get $20, $40, $60 out, but usually you don't get a whole lot more than that, right? So, for example, someone getting like $600 out of an ATM is pretty rare, right? That's going to be, atypical, right? So, if you think about it, it's going to look right skew, right? So in other words, we would say no, it's not normally distributed, right? So no, the variable ATM withdrawal is likely skewed right. Right. So in that case, since my population is skewed, I'm going to want the sample size to be greater than or equal to 30 then, right? So in part B, it says if a random sample of 50 ATM withdrawals is obtained, describe the sampling distribution of X bar, the mean withdrawal amount, right? So in this case, n equals 50, which of course is bigger than 30, right? So the, sampling distribution of X bar will be approximately normal with a mean equal to mu, right, which was 67, right, as stated above, and a standard deviation of sigma divided by square root of n, which I know n equals 50, so I can plug that in. And the standard deviation from above, we were told to assume 35. Right? And if I round this to 4 decimal places, I get 4.9497. Okay? So then now in part C, we're asked to determine the probability of obtaining a sample mean withdrawal amount between $70 and $75, right? So in this case, we're finding area in between two values, right? So in the center is going to be the mean of 67, and then somewhere over here is going to be 70 and 75. I'm trying to find this probability, or this area, that X bar is in between 70 and 75, right? And this is a X bar distribution. So using StatCrunch to find that, you should get 0.2192. So you can verify that really quick. Just to remind you, you're going to hit the between button. The mean is 67. The standard deviation is 35. Or no, that's of the population. The standard deviation of X bar is approximately 4.9497. And we're finding in between 70 and 75. Right? Hit compute, and we get that area to be about 2192, as I said, right? And there's the computer generated graph. Right? So, if you wanted to interpret this value really quick, we could say, if we take 100 simple random samples of size n equals 50 ATM withdrawals, then about 22 of them I'll say of the samples will result in a mean withdrawal amount between $70 and $75. Right. All right. So that's all I have for this section. Make sure you let me know if you have questions. Thanks.